Good afternoon to all. I am S. PUSHPALATHA, Associate Professor in CSE Department. I am going to handle here Unix internals, in which various data structures used in the operating systems I am going to handle. This is the kernel architecture of Unix. The kernel architecture of Unix has two levels. One is user level and kernel level. The user level, the user can give his program in which he can give system calls and other library functions used in the program. In the kernel level, all main modules of the operating systems are given. The kernel level is consisting of file subsystem, buffer cache, device driver and process control subsystem. These are the main modules in the kernel level. Here the library functions in the user level or library functions that can be used in the user program, and then user program can invoke with the kernel level through the system call interface. And then the file subsystem, it is used to handle all files used in the Unix operating system. It allocates space for all the files. And then the device driver, this is handling all I/O devices, that is input and output devices. They are all hardware devices. And then the input output devices are of two types: character devices and block devices. Character devices example is keyboard. Block devices, the example is tape, disk, pen drive and CD-ROM. Okay. And in between the file system and the device drivers, there is a buffer cache module available. The buffer cache module is reading the content of the block driver and interfacing with the file subsystem. And then the process control subsystem is dealing with all processes, and it is having other submodules: interprocess communication, scheduler, memory management. Interprocess communication is interacting the processes with each other through system call. Scheduler, this is doing CPU scheduling for all processes. Memory management, so this is handling all virtual address space of the program. So as the physical memory size is limited, there is a swapping between secondary memory to the main memory. This is handled by the memory management module. So these are the main modules in which I am going to handle various data structures used in the file system, buffer cache and process control subsystem. Buffer cache is a collection of buffers. It contains two parts: memory array and buffer header. Memory array is related with data area, and buffer header is having metadata about the content stored in the buffer. The size of the disk block is equal to the size of the buffer, so that it is 1:1. Buffer header contains the metadata. The details of the buffer header are device number, block number, status, pointer to the address data area. Pointer means it is the address of the data area, and pointer to next buff to hash queue, pointer to buff on hash queue, pointer to next buff on free list, pointer to previous buff on free list. Pointer to next buff means this is a forward pointer, and pointer to previous buff means it is a backward pointer. Similarly for the hash free list also. The buffer header is containing device number. It is a logical file system number, or it is called as file system number. Block number is block number of the data on the disk block. And status, buffer is currently locked. Buffer contains valid data. Buffer data is delayed write. The kernel is currently reading or writing the contents of the disk. A process is currently waiting for the buffer to become free. The kernel identifies the buffer by examining the device number and the block number. There are two data structures in the buffer cache. One is free list, another one is hash queue. The free list is used to handle all free buffers in the buffer cache. The free list is using a basic data structure, circular doubly linked list. Buffer allocation is done in the buffer cache using a least recently used method. And any buffer becomes free, it will be added at the end of the free list. If the buffer has to be removed from the buffer free list, it will be removed from the head of the free list. since it is a queue data structure. So here the free list header is there, the header is pointing to the buffer 1, buffer 1 is pointing to buffer 2, buffer 2 is pointing to buffer n. Similarly, the backward pointer are used to refer the previous buffers. Buffer n is pointing to the buffer n minus 1, then similarly buffer 2 is pointing to buffer 1, buffer 1 is similarly pointing to the free list head. So this is a circular doubly linked list. Okay, and then the next data structure used in the buffer cache is hash queue. The hash queue is using a data structure hashing and queue. Queue is again the circular doubly linked list. Hashing is using a hash function of the device and block number to put the proper buffer in the proper hash queue. So this is the hash queue headers, and then each the hash queue is filled with using a mod 4. There are 4 blocks here, so the mod value is taken for 4, and the buffers can be arranged in each hash queue based on the mod value, and all the buffers will be connected with a circular doubly linked list. And then using these two data structures, there are some scenarios that to allocate buffers in the buffer cache. So there are totally 5 buffers. For allocating the buffers in the buffer cache, the Unix operating system is having an algorithm getBLK. getBLK algorithm. The kernel finds the block on its hash queue. There are 5 scenarios. The kernel finds the block on its cache queue. The first is the buffer is free. The buffer is currently busy. The kernel cannot find the block on the hash queue. Again, there are 3 scenarios. The kernel allocates a buffer from the free list, and attempting to allocate a buffer from the free list finds a buffer on the free list, but it is marked as delayed write, and free list of the buffers is empty. Okay, let us see an example for allocating a buffers in the buffer cache. There are 4 blocks in the hash queue. Block number 0 mod 4, block number 1 mod 4, block number 2 mod 4, block number 3 mod 4. This is hash queue header. There is another data structure here, free list. This is free list header. The buffers are allocated initially in the free list. The free list is pointing to first buffer and then pointing to another buffer like this, and again it is having a pointer to this, and backward pointers will be like this. So for example, we will consider 12 buffers here. The scenarios for the buffer allocation: the buffer is on hash queue, but it is free. Second scenario, the buffer is not in hash queue, allocate a buffer from free list. Third scenario, the buffer is not in hash queue, and buffer in the free list is marked as delayed write. Fourth scenario, the buffer is not in hash queue. But the free list is empty. Fifth scenario, the buffer is in hash queue but marked as busy. These are the 5 scenarios for allocating a buffer in the hash queue. Now we have demand for the buffers, block numbers 4, 5, 6, 7, 11, 12, 13, 18, 19, 20, 21, 10, 22, 7, etc. Okay. So initially all the buffers are allocated in the free list header. Now one by one on demand the buffers will be allocated into the hash queue. Now we take the block number 4. Okay. So we calculate the mod value for the block number 4. 4 mod 4. This is equal to, that is 4 mod 4 equal to 0. Okay. So this is a block number 0. You remove a buffer from the free list. Adjust the pointers. The free list header is now pointing to the second buffer. Now allocate the first buffer for the block number 4 so that its mod value is 0. So put it in the hash queue 0. And read the content of the disk block 4 from the disk into the buffer. Now the next block we require is 5. Now 5 mod 4 is 1. So remove the second buffer and adjust the forward and backward pointers. And for the second buffer, this is the value, block value we have to read is 5. The mod value is 1. So put the buffer in the block number 1 and read the content of 5 from disk into this buffer. Similarly, all the blocks will be assigned for the buffers. So the next buffer we have to allocate is 6. So the third buffer will be taken. The 6 mod 5 is 2. So it will be put in the block number 2 queue. The next value is 7. 7 mod 4 is 3. So put it in the block number 3. Okay. So for allocating the buffers, one by one buffers will be removed from the free list. For allocating 11 mod 4 is equal to 3. So you connect the 11th block in the third hash queue. Next 12. 12 mod 4 is 0. 3 into 4, 0. So it is 0. So you put it in the block number 2. And then 13 mod 4 is 1 and allocate in the block number 1 hash queue. Then 18. Okay. So remove buffer and then allocate 18. 18 mod 4 is 2. So allocate here in the block number 2. Then 19 mod 4 is equal to 3. So allocate in the block number 3. And then 20 mod 4 is equal to 0. So remove a buffer and allocate in block 0. 21 mod 4 is equal to 1. So put it in the block number 1, 21. So now 11 buffers are allocated from free list, and then 10. 10 mod 4 is 2. So put the block number 2. Now 12 buffers are allocated, and then the free list is exhausted. So every time we remove a buffer from the free list and add it in the hash queue. After allocating all the buffers, the free list becomes empty. Okay, so here we compare this with a scenario. Okay, removing a buffer from the first one and allocating in the hash queue. Here we take the second scenario. When initially the hash queue is empty, one by one the buffers are removed and added in the hash queue. This is similar to the second scenario. And then here, after allocating all the buffers, the free list is empty. Now we have to allocate 22. We see whether the 22 block is available in the hash queue. It is not there in the hash queue. If it is not there, we have to see in the free list if there are any free buffer available in the free list. If there is so, we have to allocate a buffer. But here the scenario is free list is empty. This is similar to the fourth scenario. So if the buffer cannot be allocated in the buffer header, the process requesting the block number 22 has to sleep until some buffer becomes free in the free list header. Then we see for the third scenario. After allocating these 12 buffers, after the process is over, some processes will release some of the blocks. For example, the block number 3 is released by some process. Then if the process is over, the contents, updated contents of the buffer 3 is written back to the disk and it is added to the free list. So it is connected with the free list header will be connected to the block number 3 and the pointer will be connected to this like this. So forward and backward pointers will be set. Now the third buffer block has come to the free list. And then the next buffer allocated here is the now 18th buffer is freed by some process. So the second buffer has to be added. When 18th buffer has to be added, it has to be added at the end of the queue. So it has to be marked like this. Okay, it is added at the end of the list. Every time a process puts a buffer in a free list, it has to write the content back to the disk. If it is postponing the content, writing the content, then it will be marked as delayed write. That is, the content is valid only in the buffer cache, but it is not valid in the disk, so that it is marked as delayed write. Then some process is releasing the block number 21. Now the block number 21 has to be written back to the disk and then it is added to the free list header. So 21 is added, so the 18 is the last node in the queue, so it is pointing to the 21 and 21 will point to the free list header. Then another block 10 is again freed, so that the 21 will be pointing to 10 and then 10 is pointing to free list header. Now 4 blocks have become free and it is added in the free list 3, 18, 21 and 10. Next we see the scenario 1. The buffer is on the hash queue but it is free. So the demand for the block number 3. There is a demand for block number 3. Now the kernel checks in the hash queue. Then if it is seeing that the 3 is available, okay, 3 is having a valid data, so that it has to be removed from the, also it is not used by any other buffer, it can be removed from the free list and it can be put in the hash queue. So this is similar to the first scenario. So the pointers to the 3 is removed. 3 is a first node. Then the free list header is pointing to 18 here. Now there are 3 buffers available, 18, 21 and 10. Next demand for the block number is 25. So now the kernel checks for 25. The 25 is not available in the hash queue. So it has to allocate a buffer from the free list and it should be put in the proper hash queue. So it has to remove a buffer, means at the beginning of the buffer only it has to remove. So the 18 is available at the beginning of the queue, but it is marked as delayed write. Delayed write means the contents are not updated in the disk. So it cannot be allocated for the 25th block, so that it has to be it has to see for the next block. So the 18 is marked as delayed write. The kernel will initiate for the asynchronous write operation. So the 18 buffer will be removed from the free list and initiate the write operation. So when the writing of the content into the disk is done, means the 18th buffer is busy now, so it cannot be allocated. Then the next buffer in the free list has to be allocated for the 25th buffer. So the 21 has to be removed. (21) is pointing to 10, so the free list header is pointing to 10 now. So the 25 mod 4 is equal to 1. So put the 25th block in the proper hash queue. Okay, like this, one node is removed from the buffer and it is added in the proper hash queue. This is similar to the third scenario. Okay, if the buffer is delayed write, it will initiate the write operation, then the next buffer will be allocated for the required block. This is third scenario. Then the block number 5 is required. Block number 5 is required. Now the kernel will check the block number 5 in the hash queue. It is available in the hash queue, but it is not in the free list. If it is not in the free list, it is busy, so that it cannot be allocated for any other process. So that the process which is requesting 5 now has to sleep. The buffers which are available in the hash queue but not on free list are busy buffers only. So this is similar to the scenario 5. So we have seen an example for all the scenarios, starting from the hash queue is buffer is available in hash queue but it is not free, and also it is busy, and then buffer is not available in hash queue, allocate a buffer from free list. It is not on hash queue, buffer is delayed write. The buffer is not on hash queue but the free list is empty. For all scenarios we have seen an example. Okay, this is a getBLK algorithm in Unix operating system. This is available as getblk.c in Unix OS. This is explaining all 5 scenarios. So far we have seen with an example. Here the input is logical device number and block number. The output is locked buffer. While buffer not found, if the buffer is in hash queue, there are 2 conditions. One is buffer is free and another one is buffer is busy. So first one is, if buffer busy, it has to go to sleep and continue. This is similar to scenario 5. If the buffer is not in hash queue, Okay, mark buffer busy and remove a buffer from free list, return buffer. This is similar to scenario 1. Else, if there is no buffer on the free list, the process has to go to sleep and continue until a buffer becomes free. This is scenario 4. Remove buffer from free list if buffer marked as delayed write and it initiates a asynchronous write for the buffer to disk and continue. This is scenario 3. And remove a buffer from hash queue, put it in proper hash queue and return buffer, scenario 1. So all 5 scenarios are given as algorithm getBLK. Okay, this is for allocating a buffer. And then when a buffer is released by any process, it has to be added in the free list. So while adding the buffer in the free list, the algorithm is brelease, BRELSE, the brelease algorithm. The input is lock buffer, output is none. So when a process is going to add a buffer in the free list, it has to wake up all sleeping process for this buffer to become free, or any buffer to become free will be woke up, and wake up all process even waiting for any buffer to become free, and wake up all processes even waiting for this buffer to become free, and raise processor execution level to block interrupts. Here we are going to add a buffer to the free list. Free list is using a circular doubly linked list. It is handling 2 pointers, forward pointer and backward pointer. While handling pointers, the interrupt should not be handled by the kernel, so that it has to raise the processor execution level to block other interrupts. If buffer contains valid and buffer not old, NQ buffer at the end of the free list, else NQ buffer at the beginning of the free list. This is similar to the delayed write scenario. And then after adding the buffer to the free list, it lower processor execution level to allow interrupts and then unlock the buffer. Now the buffer is added in the free list. And then we will see about the file subsystem. The file subsystem is used to manage files, allocate file space, administering free space, controlling access to files, retrieving data. The data structures used in the file subsystem are user file descriptor table, file table, inode table. The user file descriptor table is a per process table. File table and inode table are global tables. The user file descriptor table is created for every process. The example system calls for handling the file system data structures are fd1 is equal to open /user/f1.c read only mode. fd2 is equal to open /user/f2.c read write mode. For handling these two system calls, how the data structures are used, we will see. The first file is f1.c, it returns the fd1 descriptor. The second file is f2.c, it returns the file descriptor fd2. The first file is open in read only mode, the second file is opened in read write mode. The user file descriptor table is a per process table. In the same process, we have given two system calls open, so that only one user file descriptor table is available here. The index of the user file descriptor table starts from 0, and file table is for having entries and inode table is having entries. When open system call is given, the kernel will search for f1.c in the directory, it gets the inode. If the f1.c is available, it allocate an entry in the inode table. So the user /f1.c is added, and then the reference count will be added, that is one process is using this file, so that the count will be 1. Then one more entry is created in the file table for the same file. And in the file table, we give the count value and what are the access permissions. So the access permission for the file 1 is read. So that is marked here. And then one more entry is created in the user file descriptor table. In the kernel finds the first empty entry in the file descriptor table. So the first empty entry is 0 here. So it will take that entry and mark a pointer to the file table entry. File table entry will be pointing to the inode table. So these are the entries will be made for the open system call f1.c. And then the index 0 value will be returned to the user program as fd1 as file descriptor. For the second system call, then f2.c is the second system call. So if the second file f2.c is available, it has to allocate an entry in the inode table. The inode table, again it marks the file name and then what is the count. Only one process is using this file, so the count is equal to 1. Then it has to create an entry in the file table. File table for the f2.c count 1, it is read write mode, that is marked here, and make a pointer to the inode table. Then again it will find a entry in the next empty entry in the user file descriptor table, that is pointing to the file table. File table again points to the inode table. So this link will be used for identifying f2.c. Now for the f2.c, the file descriptor is 1. The index value of the entry will be returned to fd2. So these are the data structures are used in the file subsystem to handle the files, how to read, write and how to close, everything will be done. When closing, all the entries will be freed from the file table, inode table and user file descriptor table. Next we see about the process subsystem. Process is an instance of a program during execution. The process consists of text, data and stack. While execution, the process will be taking 3 portions: text, data and stack. Text is nothing but the instructions available in the user program. Data is nothing but global and local variables defined in the program. Stack is during the execution, some temporary values will be stored for the context switch. So for these 3 information, a memory has to be allocated for the process. Then many processes can run simultaneously and several processes may be instance of one program also. For handling the processes and many processes simultaneously, it uses various data structures: process table, per process region table, U-area and region table. Process table and region table are global tables. It is common for all the processes available in the Unix OS. Per process region table and U-area are defined only for the particular process. For every process, these 2 tables where data structures will be created. Process table keeps track of an entry for a process. Every process is taken for execution. One entry is created in the process table. Then U-area. The U-area is an extension of the process table. And then the process table is pointing to the per process region table. This is having 3 portions, one for text, one for data and one for stack. This has the starting virtual address of text, data and stack. Again these 3 things will be pointing to the region table. The region table is pointing to the actual addresses of the text, data and stack. And user file descriptor table is having information regarding the process. The process table entry contains state field and user ID. U-area is the extension of the process table entry. Fields of the U-area contain pointer to process table entry, file descriptors are all open files, current directory and current root, IO parameters, process and files is limit. Kernel can directly access fields of the U-area of the executing process but not of the U-area of the other processes. When a process is completed, the U-area will not be active. And per process region table entries describes whether it contains text, data or stack, and it is shared or private. Some common data can be shared by more than one process. Private data cannot be shared. That information will be available in the per process region table. The extra level from the per process region table to kernel region table allows independent processes to share the regions. And then if two processes are sharing the regions, we will see with an example of fork system call. The nature of the fork system call function is to create a child process. In the parent process, when you give a fork system call, it will create a child process. The child process will use the address space of the parent process, so that it is using some common data, and then the some data will be local to parent and local to child. For this we will see one example. The data structures for the system call. Process table is here. One entry is created for the parent. When parent is creating a child process, the another entry is created, that is child. Parent is pointing to region table. This rectangle is for only the parent process. Here we have a region table and U area, and another rectangle, this is for the child process. Here we have a U area and region per process region table. So each process is having its own region table and its own U area. Then the common region table is available here. This common region table again pointing to the memory space for the stack data and text. So the parent and child processor sharing the same instructions, the text portion can be shared by the child process. So the region table of the child process is pointing to the text portion, and then region table of the parent is pointing to the text portion here. This area is shared, but other areas stack data of the parent process is separate, and stack and data of the child process is private. So only the text portion which is shared by the same program, so that the parent and child process can share the same area, so that the memory will be consumed, but the local variables of data and stack cannot be shared. So these are the data structures help in the process subsystem to handle various processes. So everything is available as the source code, .c source code in the Unix operating system, and the Unix operating system is an open source. So by studying the source code of the C program, we can get into familiar for writing a code for any operating system. Okay, so far we have discussed about the data structures used for file subsystem, process subsystem and buffer cache of the Unix operating system. The buffer cache is consisting of two main data structures, hash queue and free list. This is for allocating buffer from the buffer cache for the disk block required. And then file subsystem is consisting of three data structures, file table, inode table and user file descriptor table. User file descriptor table is a per process table, and file table and inode table are global tables. These tables are handled by the file subsystem for open, read, write, close and seeking the content of the particular byte from the file. And then process subsystem is having four data structures, process table, U area, per process region table and region table. The U area is containing the information regarding the processes. U area is a extension of the process table. Process table is again pointing to the per process region table. Per process region table is having all virtual addresses of the text, data and stack portion of the process. The per process region table is pointing to the region table, and the region table is pointing to the memory. So these are the data structures helps in the process subsystem to handle processes for the execution.